Hi everyone, and welcome to this week's Udacity Deep Reinforcement Learning Nano Degree weekly webinar. This week I'll be focusing on PyTorch, basically just an introduction. So if you have a good understanding of PyTorch, this is probably not going to be the best for you, but if you're new to PyTorch or want to understand just the basic syntax and how to build a neural network and do some basic training, this will be the perfect webinar for you. I find that a lot of the students have a strong background in TensorFlow, and PyTorch is a bit new to a few of them. So, what I'll be covering is the basic operations, a bit about PyTorch itself. Like I said, explain construction of neural networks, training, and just go through some examples. So what I'm going to start off with, just explaining PyTorch itself. So basically in this webinar, you'll be introduced to PyTorch, which is a framework for building and training neural networks. PyTorch, in a lot of ways, behaves like arrays you love in NumPy. So NumPy and what PyTorch can do are very similar, and they will work very similar together as well. So basically, these NumPy arrays are just tensors. So tensors and arrays are pretty much the same thing. What makes the difference between a tensor is that it allows GPUs to move them faster in processing, mainly for neural networks. It also, PyTorch provides a model that automatically calculates gradients for backpropagation, which is essential for neural networks and training. And basically, the one great thing that PyTorch has, let's say, over TensorFlow, is that it's more coherent with Python and the NumPy and Stat. But this may change a bit in TensorFlow 2.0. But PyTorch at the moment is definitely much, I would say, easier. Now, what is a tensor? So a tensor has specific meaning in physics or computational mechanics. However, it has nothing to do with a tensor in deep learning. In my understanding, tensor in deep learning is just a generalization of matrix, which can be any size or dimensions. In both PyTorch and TensorFlow, tensor is represented as an n-dimensional array of base data types. So for example, here, we create an array with the following way, so just making it of ones, 5 by 3 with a d-type float. And as you can see, in NumPy it comes out of that, and there's a tensor, which is torch.ones, 5 by 3 with a d-type torch.float 64. It pretty much looks identical. The only difference is one has a tensor, but they pretty much have the same data. Now, why do we need tensors for deep learning? Why not just use NumPy arrays? There's no theoretical difference between a NumPy array or whatever arrays and tensors, but when the people invented TensorFlow or PyTorch, they defined a class called tensor. Tensor has the similar properties as a regular array, but it also has auto-differentiation, which is a critical part of backpropagation. I'll introduce that a bit later, but at this time, they coded the libraries to work with, say, the CUDA or CUDA DNN in NVIDIA, and therefore it requires a tensor and not a NumPy array. So I'm just going to go through some basics of a tensor operations within PyTorch. So for example, tensors are similar to NumPy arrays, as I said before, with the addition of being able to use GPU accelerated computing. So for example, here if we import Torch, and to construct a 5 by 3 matrix uninitialized, we would write x equals torch.empty parentheses 5 by 3, which would give us a 5 by 3 array, which is empty, just all zeros. That's the output there. Next, we'll just go on to some other ways of constructing the matrix. So if you go x equals torch.rand, 5 by 3 as the argument, and you print that out, you get a tensor with a 5 by 3 shape, which basically has all random values. So if you wanted to construct it a bit like what you can do with NumPy, filled with zeros, with a particular d-type long, you would go x equals torch.0 and arguments 5 by 3 and also d-type equals torch.long. And if you print that, you would get a tensor, a long tensor, which is basically 5 by 3. So another way to construct a tensor is directly from data. So for example, x equals torch.tensor, parentheses, and then basically adding in, like you would with an array, say the numbers. If you print that out, you're going to get a tensor with those, say 2, or whatever amount of input that you would like. Create a tensor based on an existing tensor. These methods will be reused properties of input tensor. So for example, if we created x equals x.new1s by 503 d-type, and we print that out, it brings us a tensor with all ones. Now, if we get that and change x equals torch.round light and input x, it overrides the d-type, and basically now we have, but it's the same size, so it's just change the d-type. Now, one of the things that you'll use a fair bit is probably to get its size. So if you go print and then x.size, parentheses, like call it, you will get the size which shows the shape if you're thinking about numpys. There are multiple syntax for operations. In the following example, we would like to look at the additions operation. So for example, here we've got y equals torch.rand 5 by 3. And if we go print x plus y, simply adds the tensor together. We can also use torch.add with 2 parameters, which will do the same thing. As you can see, the output gives you a tensor. Addition of providing output tensors and arguments. So, for example, result, if we get torch.empty 5 by 3, which will create an empty, just plain array with a 5 by 3 shape, and we go torch.add x, y, out is the result, and we print that, we get a tensor with the following result. We can also add x to y in place. So say we had y.add with in place, which is an underscore, and then supply x, and we print y, it also addition is in place. Now that's something I'll quickly talk about. So any operation that mutates a tensor in place is postfixed with that underscore. For example, x.copy underscore parentheses y, or x.t underscore will change x. You can use standard NumPy like indexing as well with Torch. So for example, if we index with 1 and output that, that's what you'll get. Resizing. So if you want to resize or reshape a tensor, you can use torch.view. So if you get x equals torch.rand n, give it 4 by 4, and as you can see now, if we print them out, it will give us the with the size, which gives us the shape. Basically, that will give us what we inputted there, as you can see. If you have one element tensor, use .item and call that to get the value of Python numbers. So x.torch.ram1, print x, x.item, you'll see that you get the same, just the actual details themselves. So one of the things about PyTorch is it needs to, and torches for torch tensors especially, they need to be able to work with NumPy arrays and vice versa. In Torch, tensor and NumPy arrays will share their underlying memory location, and changing one will change the other. So, for example, if we get a equals torch.1, so we construct a tensor and printer, you can see that we've got a one-dimensional with 5 ones, array with 1, or tensor with 1. If we get b equals a, so the a that we can just constructed, dot NumPy, and print out b, it has the same details. So it's taking that from there. Now, if we get a.add in place and print a, you'll see that, but also if we print b, it just changed that as well. So as you can see, they're sharing. Now, See how changing the numpy array changes the torque tensor automatically. So if we import numpy as numpy and construct a with numpy.1s and b torch from numpy, so we're now getting that numpy array, and we're using from numpy from torch with that as an argument, and we get numpy.add, and basically we print that out. As you can see, it has got that numpy array that we've constructed, and it's now got a tensor with the same details. Now this will show you it in a bit of code. So as you can see, we've printed it out, same thing from numpy, and it's the same basically values. b.numpy, the same values. The memory is shared, and if we multiply PyTorch tensor by 2 in place, we can see that we get that changes. So the numpy array matches new values from the tensor. Now, probably another thing is tensors can be moved onto any device using the .to method. So this will allow you to use GPUs. So as you see, device equals torch.device with a CUDA argument. So to device, for example, here, and that will basically, if you print the 2, you can see that it's going through the device CUDA.0, which would be pretty much probably your GPU. Now, probably the main thing that you guys need to use PyTorch with would be neural networks. So I'll just go over a neural network quickly. In deep learning is based on artificial neural network, which has been around since the 50s. So it's built on approximating neurons, typically called units or simple neurons. Each unit has some number of weighted input. These weighted inputs are summed together, a linear combination, then passed through an activation function to get the unit's output. Neural networks can be structured using torch.nn package. Now that you have a basic glimpse of this, and as you can see, here's a basic network that classifies digit images, and this is what it would look like. So it's getting the image in, and it's feeding it through and giving us the results at the end. Now, building a network with PyTorch. So PyTorch provides a module NN, as described before, that makes building networks simple. Here, on the right-hand side, I have constructed a network with an input of 784, 256 hidden units, and 10 outputs. Now, if we go through that, I've constructed inputs to the hidden layer, which has got 784, then goes to its output is 256, which then gets into the next layer, which sees 256 and outputs 10, which is the 10 different digits. Then, for example, has a sigmoid function from NN, which we'll go into more detail later, softmax, and then it basically needs to pass that all through the network in a pass, and then returns the results. So I'll break this down into more details. So class network, which takes in NN module. Here we're inheriting from NN module combined with the supernet. This creates a class that tracks the architecture and provides a lot of useful methods and attributes. It is mandatory to inherit from the NN module when you are creating a class for your network. The name of the class itself can be anything. Next part was the self.hidden equals nn.linear, which takes 784 and 256 as an argument. This line creates a module for a linear transformation with 784 input, 256 output, and assigns it to self.hidden. The model automatically creates the weight and bias tensor, which we use the forward method. You can access the weights and bias tensor once the network net is created, and this is by net.hidden.weight and net.hidden.bias, which I'll show you next. Self.input, so output equals NN linear. So this is basically taking the output from the last one, 256, and then similar, this creates another linear transformation with 256 with an output of N, as I said. Now here, we define the operations for the sigmoid activation and the softmax output. We're setting the dim equals 1, and nn softmax dim calculates the softmax across the columns. The forward method creates, basically takes a tensor x and passes it through operations you defined in init method. Now, within that method, basically here the input tensor x is passed through each operation and reassigned to x. You can see that the input tensor goes through the hidden layer, then a sigmoid function, then an output layer, and finally a softmax. It doesn't matter what you name variables here, as long as inputs and outputs of the operation match the network architecture. The order in which you define things in the init method doesn't matter. You need to sequence operation correctly in the forward method. Now, once you've done that, you would just go model equals network and call it, and then your model is basically, as you can see, it's got all those features. Now, the other way of building a network PyTorch is use nn functional as f. So you can define a network somewhat more consciously and clearly using the torch.nn functional module. This is the most common way you'll see a network defined, as many operations are simply element-wise functions. We normally import this module as f. Example, torch.nn functional as f. As you can see, we've done that, and then we have constructed, which is a bit more simple layout. So we've got the hidden, got the output, and we forward it through, which is very straightforward. Basically takes that one, takes the hidden in the sigmoid, spits it out, and then the x and the output basically go into the softmax. So far we've only been looking at the softmax activation, but in general, any function can be used as an activation function. Only requirement is that for the network to approximate a non-linear function, the activation function must be non-linear. Here are a few examples of common activation of hyperbolic tangent and rectified linear unit or ReLU. In practice, the ReLU function is used almost exclusively as an activation function for hidden layers. So, as you can see here, I'm going to basically build a network with 784 input units, a hidden layer of 128, activation, then a hidden layer with 64 units, and a ReLU activation, and finally an output layer with softmax activation as shown below. So as you can see, I've got the first connected layer takes in 784 and spits out 128. The second fully connected layer takes in 128 and spits out 64. And the third, the output layer, takes in 64 and spits out 10. So in the forward pass, basically takes that, we ReLU it, so X goes through the connected layer, then gets a ReLU, spits it out, goes back into the next connected layer, ReLU, connected layer, softmax, and then it returns it. So pretty simple, you know, for a basic sort of network. If you print the weights, for example, from that, this is what you'll probably see. So, you know, one thing is weights are automatically initialized, but you can actually initialize them manually if you want, which I'll show you next. So, for example, you can do a custom initialization to fill the zeros. You can also do so sample from a random normal to a standard dev, say 0.01, and you get it out like that. Now, next, what you do, so now that we basically have a network, let's see what happens when we pass it an image. So basically what we've got here is we've got train loader, so and we've taken in an image and labels. We resize it into a 1D vector, convolution, and we forward pass this through the network. You can see it model.forward through, and then where, as you can see, the probability using a helper function basically comes out with nothing because it hasn't been trained. Now, that's all good, but there's probably another easier way of, and another way that you can use to create a neural network in PyTorch, which is NN sequential. So PyTorch provides a convenient way to build networks like this, where a tensor is passed sequentially through operations, say dot sequential. You can look up more. So for example, here we're defining the input size 784, the hidden size 128 and 64 as an array, and the output size 10. So what we've done here is we've used model equals NN sequential, and then as an argument we're putting in the non-linear, the input size, which takes from that, and the hidden size, which grabs the first one, and then it grabs, for example, puts the reload linear of that, and then takes the 64, then a reload and takes the 64 and outputs the output size of 10, and then does a softmax. So for example, here, if we get those images and we put them through, resize it first and forward it through the system, this is what we get as well. So it works just the same as the last one. Okay, so the other thing with NN sequential, available by passing appropriate index. For example, if you want to get the first linear operation and look at the weights, you would use model.0. So we get the first bit, as you can see here with the outputs. You can also pass in an order dict to name the individual layers and operations instead of using the incremental mixtures. Note that dictionary keys must be unique, so each operation must have a different name. So here we've got different using an order dict. So we've separated it all out, and that gives us actually more details of what we're actually doing rather than writing it out previously. Now, I'm just going to go show you how quickly you can construct simple systems. So I'm getting a lot of classes there. For example, a function to show an image. I'm just quickly creating image show, so we can show the images. Get random training images from a train loader. And here I basically construct a convolutional network, which I won't go into details here, which you can go into later yourself. But basically, first layer is a convolution layer, 3 filters for RGB and size filter of 6 by 5, which is followed by a max pooling layer, which comes from NN. So all this comes from NN. When we define a network, we need to pay more attention on the size of each layer. For example, the output dimension of the last fully connected layer is 10, which is the number of classes I had earlier. The outer dimensions of F2 and the input dimensions of F3 are identical. More details can be seen in PyTorch docs. And basically, this is what you would get from 3 epochs. So it didn't work very well, but it hasn't had enough training. Now, I'm going to go into actually training a neural network. So that was just a little demo, but back to where we were before. We just constructed using sequential, NN, and functional. So the networks we built in the previous, basically, we're very similar. They don't know anything. Neural networks with nonlinear activation work like universal function approximators. There is some function that map your input to output, for example, images of handwritten digits to class probabilities. The power of neural networks is that we can train them to approximate this function, and basically any function given enough data and compute time. So I'm going to talk about losses. Let's start by saying how we can calculate the loss with PyTorch through an NN module. So PyTorch provides losses such as cross-entropy loss, NN cross-entropy loss. We usually see the loss assigned to a material. So here, as you can see, get the training set, constructed a basic model, we define the loss, we get the data, we put it through, and we forward pass it through and get the logits, and then the logits are fed into the loss with the labels, and that will get you your loss. So basically here, I'm building a model that returns the log softmax as an output and calculates the loss using a negative log, likelihood loss. So once again, construct a basic, we set the loss images, and we forward pass and get log probabilities, then we put those logs and get the loss. up. That's not going to do anything unless we've got autograd. So now that we can how to calculate loss, how do we perform back propagation? That's essential, of course, otherwise the loss is going to be useless. Torch provides a module autograd, automatically calculating gradients of tensors. We can use it to calculate the gradients of all our parameters with respect to loss. Autograd works by keeping track of operations performed on tensors and then going backwards through those operations calculating gradients along the way. To make sure PyTorch keeps track of operations on tensors and calculates the gradient, you need to set require_grad equals true on a tensor. You can do this at creation with the require_grad keyword or at any time with x.require_grad underscore parentheses true parentheses. So you can turn off gradients or block code with torch.no_grad, for example, as seen here. You can also turn off gradients altogether with torch.set_grad enable true or false. Gradients are computed with respect to some variable z with z.backward. This is the backward path through the operations that created z. Below you can see the operation that created y as a power operation, powered backwards. So as you can see, the autograd module keeps track of these operations and knows how to calculate the gradient for each one. In this way, it is able to calculate the gradient for the chain operation with respect to any tensor. We reduce the tensors to y to scale. So, as you can see, there it goes. z.backwards, x.grad, and there you are. But what you really need to do is use these two together. So when we create a network with PyTorch, all of the parameters are initialized with require_grad. This means that when we calculate loss and call loss.backward parentheses, the gradient for the parameter are calculated. These gradients are used to update the weights with gradient descent. You can see an example of calculating the gradient using backwards pass. So as you can see, loss.backwards, and then we print afterwards. See how they've slightly changed? So basically we've constructed the model, got the loss, got the labels, images, where you get the log PS, which then is fed into the loss, to the logics. And then if we do a backwards pass on the loss, it changes that from there. It's pretty cool, right? There's one last piece that we need to, before we start training, an optimizer. So that's we'll use and update the weights of the gradients. We get these from PyTorch optim package. So import optim. So for example, we can use stochastic gradient descent with optim.sgd. You can see how to define an optimizer below. Now that we know how to use all the individual parts, it's time to see how we work together. Let's consider just one learning step before looping through all the data. So we're going to make a forward pass through the network, use the network output to calculate the loss, and perform a backwards pass through the network with loss.backward to calculate the gradient. Now take a step with optimizer to update the weights. And we can see here, if we've got those, we've already got the model, and we resize the image, and we've defined basically the optimizer, so clear the gradients because gradients are accumulated, and from there we forward pass, then backward pass, then update weight. So the output of the model, given the images, goes into the as an argument for the loss, and then the loss does a backwards pass, and as you can see, they have changed in the outputs. Now, basically we take an update step and view the new weights. So, for example, here, updated weights, we do a step. Now, what we're going to do now is train something for real. So we're actually going to make a loop as well. So now that we've put the algorithm into a loop, as you can see here, we can go through all the images. So basically we've constructed the model as we've done before using sequential because it's simple. We've created the loss, the optimizer. And so here the loop basically in range, there are 5 epochs, to a running loss of 0. So it inputs, gets the images and labels using train loader. It flattens the images using image.shape. It then basically use 0 grade with the optimizer, and then it basically goes output equals model.image, same as we did before. Loss takes the output, which then we run backwards on the loss, and then we use the optimizer.step, and then we get the running loss. So you can see here, it gets lower and lower and lower. Pretty impressive and very simple. Now, if we plot that out, you can see that it can pick up a 6 quite well. If, for example, we trained it for a bit longer than we just trained it, but as you can see, it was then able to output, if we pass it through, the details of what's going on. It's using a helper class, but this sort of gives you the basics of PyTorch. So what you'll be mainly using in deep reinforcement learning is the architecture. You'll probably be using squeeze as well, so have a look about that, and unsqueeze. But the basics you'll need to construct a neural network. If you understand that, you can look into the docs and understand more as you go along. So that's pretty much all for PyTorch this week. It's probably, you can go into more detail as we go into the docs, but the main thing I just wanted to do was get through the basics for everyone and just explain what's going on. So, all right, well, thank you very much for listening, and I will talk to you guys another time.